Okay, so I guess you would be familiar with the network computing, which is offloading parts of applications from hosts to the network switches, with quite a few instances from recent years, showing improvements to application performance. Given that, why aren't major cloud providers offering network computing as a service to their tenants? In fact, we'd argue they're missing out on an opportunity to provide some useful applications. This includes precise monitoring and performance debugging, low latency services like consensus, key value caches, application-specific load balancing, and more. We believe there's one main reason why this is the case, which is that existing hardware switches don't provide the ability to run multiple isolated applications, fault isolation between different programs, the ability to prevent one program from affecting the performance of others or the rest of the network traffic. We'd also need the ability to load and unload programs at runtime without affecting the network. And last, we would need the ability to constrain tenants to their own virtual networks. In the rest of this talk, I will introduce the concept of SwitchVM as a solution to this problem. We'll later discuss some challenges in the implementation of this design. We'll discuss the design, the implementation itself, and eventually the evaluation results. SwitchVM is what we call an in-network computing secure sandbox. On one hand, we allow tenants to write whatever programs they wish. We call these programs DPFs, data plane filters. We'll see later why. DPFs can essentially operate only on the tenant's packets, and they can access state from the packet itself or from switch memory, perform simple computations, and affect the forwarding of packets as long as it's within the tenant's virtual network. The operator, on the other hand, simply controls the DPF execution permissions using per-tenant policies. Let's take a look at a typical deployment scenario of SwitchVM. Say some tenant wishes to count packets of a specific flow from A to B, and for some reason they wish to send every 10th packet to a different host, C. In SwitchVM, tenants request placement of this DPF from the operator. The request itself is expressed relative to the tenant's virtual network, and the operator's job is to do the actual placement on the physical topology, taking all of the tenant's VMs into account. Switches that don't need to operate on the packet simply forward them as usual. The operator then needs to allocate memory to store the counter. They need to install virtual to physical mappings to get to host C. And last, they need to load the DPF code into the relevant switch, or alternatively, authorize execution of DPFs from the packet itself. Now, the key to implementing the sandbox is to use language-level virtualization. The DPFs themselves are implemented in a unified SwitchVM ISA instead of the switch's native language before. This is just a RISC-like ISA with a few additional instructions specific to SwitchVM. It's actually Turing-complete, which I will discuss later. SwitchVM in this case simply acts like an interpreter to these instructions, which get translated to the switch's native operation. It basically loads DPFs per packet and executes it. The DPF's compliance with the sandbox policies is enforced at runtime, according to the rules installed during setup. SwitchVM is actually inspired by the Linux eBPF. The ISA is quite similar. But unlike eBPF, we have runtime enforcement instead of static verification. Next, we'll discuss challenges in designing and implementing SwitchVM. We chose to implement SwitchVM on RMT pipelines based on the PISA architecture, specifically in Intel Tofino. The pipeline, as you might know, is built from a number of stages. Each stage has a number of match action tables that can be applied in parallel. Each stage has its own on-switch memory that can be accessed by the program. Packets traverse the pipeline in a forward direction only. And if each packet does it once, then the processing happens at line rate. As a result of this choice, we need to implement the pipeline using P4, with match action tables. This includes the ISA and all of the sandboxing logic. Last, match action tables can't be modified at runtime in Tofino, so we can't add or remove tables. But what we can do is to modify table entries. All of these challenges have quite some implications on the way we design SwitchVM. First, the ISA needs to be implemented with match action tables. So we use the ISA opcodes as the match keys, and the action just decides what operation to perform, which means every instruction is eventually mapped to a hardware operation. Because we can't add or remove tables, the same match action tables need to be shared by all DPFs. The DPF just decides which actions are executed at each table. And DPFs need to be stored in switch memory, either as match action table entries, or instead of being stored at a switch, they can be embedded into the packet itself. To get as much of a single pass through the pipeline as possible, we need to utilize the intra-stage parallelism. So we need a very large instruction word architecture, meaning we bundle up a few ISA instructions together and execute all of them at a single stage. To utilize the multiple stages of a pipeline, multiple wide instructions need to be executed consecutively, one after the other, on consecutive stages. Each instruction just modifies the registers and passes them on to the next stage. Now, next I'll move to the design of SwitchVM. First is how should a SwitchVM packet look like? Since we're discussing data center networks, we can use the virtual network identifier from the encapsulation headers to identify different tenants. This is used for enforcing authorization and isolation. SwitchVM-enabled packets hold a new encapsulation header option. It holds a pointer to the DPF code, which might be in the packet itself or stored inside the switch. It also holds a data stack, which the DPF uses for its inputs and outputs. The header structure is the same for all applications, so we can't really define new headers for different applications. Let's see how the data plane flow looks like for a packet. SwitchVM-enabled packets entering the pipeline first go through the filtering stage. According to the DPF placement, during setup, the module decides if the packet DPF should be executed or not at this specific switch. Packets that aren't authorized to execute at the switch are simply forwarded as usual, because they might need to be executed somewhere else. This is the first part of the secure sandbox. Next step is the prologue. In this stage, the input registers for the DPF program are initialized. This is actually the first part programmed by the tenant. These inputs can come from either the in-packet data stack or the switch metadata if authorized by the sandbox. The actual DPF execution is performed using a pipeline of execution units. Each unit actually performs a VLIW instruction. The number of units in the pipeline limits the number of instructions in a DPF, and the number of tables in a single stage limits the number of instructions executed in parallel, which is the VLIW width. Each execution unit has access to stage local stateful memory using virtual memory mapping. This memory is allocated by the operator in the setup phase, which is the second part of the secure sandbox. Every access is checked at runtime to ensure resource isolation. DPF code is loaded before each execution unit for that specific execution unit. This allows two things. First, it allows us to implement conditional branches from the ISA by comparing registers and fetching the next execution unit's instruction. Second, the code can come from either the switch memory or the packet itself, which can be mixed together. Last step would be to return data back into the packet during the epilogue if needed, as well as apply any forwarding operations that DPF might result with, as long as they're installed during the setup phase, which includes mapping from virtual to physical addresses. This way, the operator can control the forwarding operations and make sure that the tenant stays inside their own virtual network at all times. Since the number of stages limits the DPF size, we might need to have larger programs that span multiple DPFs. First way to do it is to use recirculation. We can modify the program identifier at the epilogue, at the last stage, to point to a different program in the same switch, and then just recirculate the packet. In this sense, DPFs are Turing-complete, so we can, in principle, implement things like bubble sort entirely in the data plane. Second way is to modify the pointer to DPFs in a different switch. This way, we can chain multiple functions, one after the other, across the network. Now I'll discuss some implementation aspects of SwitchVM. Execution units, as I said, are VLIW units built entirely out of match action tables using P4. Instruction opcodes are just keys for these tables. This added layer of virtualization, of course, adds some resource usage overhead over simply implementing applications in P4. Each unit is built over 2 pipeline stages of the switch. The A's and B's are just the pipeline registers, and each unit performs a number of ISA instructions at different parts. First, we have the data movement between registers done in the first stage within the selection tables. In the second stage, we have the stateless ALU instructions like additions and binary operations. So say to add 2 registers, we first move them to a specific lane in the first stage and then apply the addition operation during the second. Virtual memory is accessed on 2 stages as well. We have the address translation in the first stage and the actual access during the second. This includes load, store, and some read, modify, write operations. Control flow also spans 2 stages. First, we compare registers for conditional branches, and then we fetch the code to the next execution unit. More details can be found in the paper. The SwitchVM pipeline is mapped directly to a match action table pipeline. Filtering and prologue each take 1 stage, the first 2 stages. Each execution unit spans 2 stages, and the epilogue and forwarding each take up the last 2 stages. And the main challenge is actually to make it all fit within a pipeline. We need to implement as much execution units and as much instructions in every single stage. In our prototype in Tofino, we have 4 execution units, meaning 4 VLIW instructions per pass. Each wide instruction has a few ISA instructions of each type. Since we wanted to cram as much logic as possible into the pipeline, the resource usage is relatively high. The ISA, of course, is not compatible with P4. And in addition, the parser itself is not programmable, so we can't add new headers for different applications. Last, I want to show some evaluation results. We implemented the prototype for SwitchVM using P4 on Tofino. We implemented a few applications from recent works on in-network computing, including load balancing, consensus acceleration, key value cache. I'll show the runtime reconfigurability evaluation with a load balancing example, and the rest of the evaluation results can be found in the paper. Now consider a system with a bunch of clients and servers of some application. What we wish to do is to have some load balancing between those servers, and we wish for it to be load aware. What we would like to do in this application is to have the switch store an estimate of the load on every server. This can be done using a DPF on the responses, which simply updates the switch memory location for that specific server's load. Then we need requests to use a DPF that uses the least loaded one. Since the number of instructions can be large, we implement power of 2 choices, which means the request DPF samples 2 random servers and uses the least loaded one. The reconfiguration experiment goes like this. We have the response DPF, which constantly updates the server load on the switches. And we have the request DPFs, which can switch between two different policies, one load oblivious and one load aware. Each policy is just a DPF that the client can implement, which can be part of the packet or pre-deployed on the switch. And we measure the 99th percentile request latency over time. At first, we start with the load oblivious policy, where the request latency is high. Then we switch to load aware one. And the first thing we notice is as expected, we get a latency improvement. Second thing which we don't see is that we record no packet loss during this transition. Last, we return the load oblivious policy, and we observe no packet loss again. We have all the details of this atomic reconfiguration procedure in the paper, where we also have additional in-network applications that we either implemented or sketched. There has been some work, of course, on running multiple programs on the same switch. First approach is to have a P4 hypervisor. This is similar to what we did, but with P4 instead of a different ISA, which makes it incur high performance and resource overhead. Second is to merge multiple programs at runtime, which requires to space partition all of the resources and recompile when we need to make changes. Third is to just design new hardware with dedicated isolation support. To conclude, SwitchVM provides an in-network computing secure sandbox and gives tenants access to in-network computing in multi-tenant environments using existing switches. And with that, thank you, and I would be happy to take questions.